Hello, in this video we study elementary matrices and we learn how to use matrix multiplication to realize row operations. And then we study LU factorization of a matrix and how to apply this to solve a system of linear equation. The main purpose, as I mentioned several times, is to solve the system AX equal to B, right? And right now we know at least two methods how to solve that. The first method use elementary matrices. No, use elementary row operations, right? So we have Gaussian elimination, right? Or Gauss-Jordan elimination. That is the first method. So the second method is if your matrix A, the coefficient matrix is square, right? And invertible, so you can use inverse matrices to solve this system, right? Let's say use inverse matrix. But again, right, these two methods cost expensively. In the case that, a lot of operations, if you look at this from the point of view of computation, right? So, each operation takes amount of time, right? So you just calculate all operations to solve the system. You have a complexity of that, algorithm. So it turns out that these two methods are expensive in the sense that, you need a lot of operations to finish the algorithm, okay, to solve the problem. That's why even, system of linear equations is well known, but right now people are still working on how to solve such a system faster. Because in the real life, you might have matrix of very big size. So, it's challenging, okay? And today, we learn one more method. That's, use LU factorization, okay? Anyway, let's start with the row elementary operations. We know three row elementary operations. The first one, when you interchange two rows. When you interchange two rows, you don't change the system, right? When you multiply a row by a non-zero constant, multiply a row by a non-zero constant. So you don't change the system too. Or you may add a row to another. So basically we use these three operations in Gaussian elimination, right? And Gauss-Jordan elimination. You don't change the system. So, each time when you apply this, you get a new system, and the solution set of that new system is the same as the solution set of the previous system. Okay? But of course, for computation, you need to give the computer some order, right? Because the computer will solve the system for you. Is that correct? So you need to translate into some language so that the computer understood. Does that make sense? All right, so you cannot just say, okay, please interchange two rows. Okay, computer will not understand that. So you have to realize that by some operation. Look at this. Let's just consider 3 by 3 matrix, okay? So I have I3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1. If I want to interchange two rows, so how to interchange the first and the second row? Let's say this, the first and the second row. I have the following one. If I interchange the first and the second row, I have 0, 1, 0, and here I have 1, 0, 0, 0, 0, 1. Is that correct? All right. Now, let's say if I pick some matrix A, right? Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I want to interchange two rows of A. I interchange two rows of A. Let's do this right here. I multiply E1 with the A. Okay, look at this. So I have 0, 1, 0, 1, 0, 0, 0, 0, 1 in here. And then multiply with 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What do you get? So you pick the first row and multiply with each column in here, right? You get the first row in the product. Is that correct? But when you do that, what do you get? All entries with the 0 in here, so you get 0, right? This guy with all entries in here also 0. So basically, you only multiply the second entry in here, right? With all second entries in here. Is that correct? So that means the first row of the product is nothing but the second row of this matrix A. So I can write 4, 5, 6. Does that make sense? And then you move to the second row in this matrix E1, right? Again, you only multiply the first entry in here. So basically, the second row in the product should be the first row in the A. So you have 1, 2, 3. The third row will not change because you have, 0, 0, 1 in here. You multiply 1 with all entries in each column. The third row, the third entry in each column. So that is 7, 8, 9. So if you compare this matrix with the matrix A, you see what's that? You just interchange two rows, the first and the second row in A. You see that? And how you do that? You multiply the E1 with A. And what is E1? E1 is, the matrix obtained from the identity I3 by interchanging two rows in this. You see? So, such matrix is called elementary matrix. Okay? In this case, I write E1 is called elementary matrix. In this case, E1 is obtained from the identity by interchanging two rows. Does that make sense? And when you multiply such matrix by some matrix A, so you do almost the same operation, means you interchange two rows in the matrix A. Agree? You see, that's how computer will understand you, right? So computer will do matrix multiplication. You say, okay, please interchange two rows. And computer will choose the elementary matrix for you. For example, if you want to interchange, the third and the first row in A, right? So I will interchange the first and the third row in the identity matrix I3. And then I will take that matrix and multiply with the A from the left. Does that make sense? So that matrix should be, if I interchange the first and the third row, I have 0, 0, 1. So that is the third row in the identity, 0, 1, 0, 1, 0, 0. And then I multiply with the matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you get exactly, you interchange these two guys. Okay? So computer will understand that. Does that make sense? Similarly, you may define elementary matrices that realize, multiply a row by a non-zero constant and add a multiple of a row to another. So basically, you always start from the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. You want to multiply the first row of some matrix by some number. So you need to make an elementary matrix from the identity, right? So you say, let's say E2, you multiply the first row with 10, for example. So you have 10, 0, 0, 0, 1, 0, 0, 0, 1. And then you multiply this matrix with the A. You get exactly, you multiply the first row of A by 10. Does that make sense? If you want to add, the first row to the third row, it's pretty easy. You make an elementary matrix Matrix from the identity, right? How? That will help you to do that operation. So I just add the first row to the third. I have the following one. E3 equal to 1, 0, 0. Nothing changed with the first row. Nothing changed with the second. But the third would be 1, 0, and 1. You see? I just add the first to the third. And then I will take this matrix and multiply with the A. You get exactly in A. Add the first to the third. Does that make sense? So now we know how to use matrix multiplication, how to use elementary matrices to do row elementary operations. Okay? And then, each time you apply product, right? Elementary matrix before the matrix. So, enlarge it. If you have a matrix A and you want to get a row echelon form, right? So basically you need to apply a sequence of what? Sequence of row elementary operation, right? But that is just, a sequence of matrix multiplication. Is it correct? So you might think, yeah, the first one you apply E1 to A, and then you apply E2 to E1A, and then you apply E3, E2, E1A. Is that correct? And so on. You have different operations in here, and it depends on how many operations you need. But overall, I can write that is EM minus 1, and so on, E2, E1A, and that is what? That is the row echelon form. Even you want a reduced row echelon form, you do almost the same thing. So you apply a sequence of, matrix product between A and elementary matrices. Does that make sense? You see, now computer understands what he needs to do. Okay? Let's consider the following example. Let's find a sequence of elementary matrices that can be used to write the matrix A in the row echelon form. And our matrix look like this. That is 3 by 4. So we need to find a sequence of En minus 1, and so on, En, E1, right, A. And of course, you can guess, in this case, En should be of the size 3 by 3, because we multiply with the A from the left, right? You see, you have 3 rows in here. So, EI should be of the size 3 by 3. Okay, that means EI are obtained from the identity I3. Okay, so your matrix is not necessary to be, like square. Does that make sense? Let's do this. So look at the matrix A. We have 0 on the top, on the first row. That means, in order to find the row echelon form, you need to interchange 2 rows, right? The first and the second. Of course, you can use the third row, right? But, I see 1 in here, so I just interchange the first and the second. So I interchange the first and the second. I have the first operation would be interchange the first and the second, okay, rows. So I have A1 is 1, negative 3, 0, 2, 0, 1, 3, 5, 2, negative 6, 2, and 0. And the elementary matrix that can be used for that operation is 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is, obtained from the identity by interchanging the first and the second row. Is it? So I write E1, okay? E1 is this. And then next, you multiply the first row by -2 and add to the second. Okay, I write here, multiply the first row by -2 and add to the third. Okay, add to the third. So I have A2 is equal to 1, -3, 0, and 2. Use 0, 1, 3, 5, and then I have 0 in here, -2, add to the third, so I got 0 in here, I got 2 in here, and I got -4 in here. Okay, so I need to use the following matrix. Let's say this is E1, I have E2 is equal to, multiply the first by -2, add to the second. So the first will not change, 0, 1, 0, 0. Add to the third, sorry. The second will not change, but the third is -2, 0, and 1. Because you multiply the first row by -2 and add to the third, you see? So you have this, okay? And then next, oh, you already have row echelon form, that's it. So basically, in order to get A2, I have A2 is equal to E2 times E1 and A. Yes. You see, this is A1, right? And then you apply E2 to A1, you get A2. Okay. Of course, you know you can get the reduced row echelon form. That's okay. By another one. Okay. By using, you know, maybe I guess in this case you need to use 2 more operations. But anyway, we are already here, so let's do that. So I want to get a reduced row echelon form, so I need to divide the third row by 2, right? If I divide the third row by 2, I have the following one. A3 is 1, -3, 0, and 2. 0, 1, 3, 5, 0, 0, 1, and -2. And the corresponding elementary matrix is 3 is 1, 0, 0, 0, 1, 0, 0, 0, and here should be 1 over 2. Okay, you divide the third row by 2. All right, so now you will multiply. I will do 2 operations at the same time. Look at this. I will start from here. Since this is already 0, I multiply the third row by -3 and add to the second. Okay, let's not do that. Just do 2 operations. Sorry for that. So I will multiply the third row by -3, add to the second. I get the following: 1, -3, 0, and 2, 0, 1, 0. Here I have 11, right? And here I have 0, 0, 1, and -2. The elementary matrix is E4 equal to by -3, right? So the first row will not change, the third row will not change, and then but the second row change. Multiply the third by -3, add to the second. So I have 1 in here, but here -3. You see? And now you multiply the second row by 3 and add to the first. So I have A4 equal to 1, 0, 0. 3 add to the first. I have 33 plus 2 is 35. In here have 0, 1, 0, 11, and have 0, 0, 1, -2. The third row will not change. So the E5 should be, the third row is still there, 0, 0, 1. The second row is still there, right? But the first row is equal to the second row multiplied with 3. So I have 1 in here, 3 in here, and 0 in here. You see? Okay, overall, I will have A4 equal to E5, E4, E3, E2, E1, A. That's it. So that's how we can use 5 elementary matrices to get a reduced row echelon form from the original matrix A. Okay? So, from this example, we have the following observation. We say, yeah, properties or whatever you want to call. Maybe theorem, right? Maybe theorem. The first one, if E is an elementary matrix, then E is invertible, means E to negative 1 is X, and is an elementary. That is obvious because, you know, if you interchange two rows, you may undo that. Again, by interchange those rows, right? And, you know, multiply by a non-negative number, so you divide by that number, you just undo what you have done. So the inverse is X, and this is also an elementary. That's the first observation. The second observation, if A is square, right, and invertible, then A is product of a sequence of elementary matrices where EI are elementary matrices. This is also obvious because if A is square and invertible, means, you know, the reduced row echelon form of A is identity. Is that correct? So that means, you know, A can be converted to the identity using elementary matrices. So basically, you know, the last matrix in here is identity, right? Let's say IM. So the A is just product of a sequence of elementary matrices. You know, this is if and only if statement, means A, a square matrix A is invertible if and only if A is product of elementary matrices. Okay, so, and we still have the third statement. If you have a system AX equal to B, okay, and A is square, means the coefficient matrix is square, then this system has a unique solution if and only if A is product of elementary matrices. Is okay? Then the system has a unique solution if and only if A is product of elementary matrices. You know, basically, you know, that is very, very obvious, right, from the second statement. So, again, using these observations, we can solve this system using a sequence of elementary matrices. That is the thing we need to memorize. That's the first, right? From here, we can say, yes, we can use elementary matrices to solve the system AX equal to B. But remember that we need to get a row echelon form, right? Now let's suppose that A is invertible. Because in this case, the system has a unique solution. Let's find it, right? So in order to solve that, from A, I need to get the row echelon form. The row echelon form look like this. All entries in here will be 0. Okay, such matrix is called the upper triangular matrix. Is upper triangular matrix. Of course, since you have upper, you have lower triangular matrix, right? The lower triangular matrix look like this. Again, you have main diagonal in here, but all entries above the main diagonal will be 0. I write 0 in here. I write 0 in here. Okay? So this is lower triangular matrix. Why do we talk about this? Because you have a row echelon form. The row echelon form is an upper triangular matrix. But don't forget, A in this case is a sequence of product of elementary matrices, right? Let's say EI in here, let's say EJ, and then E1. So this is identity, right? MIM. You have to cut somewhere in here, or you might cut somewhere in here in the product. And then when you apply sequence of some elementary matrix, you get the row echelon form. Means you get an upper triangular matrix. Is that correct? So I can write here, this is some kind of U, right? Let's denote by the U. Let's denote by the U. Is that okay? So from here you have A, or you can write, from here you can write U is equal to EJ, EJ minus 1, and so on, E1A. Is that correct? And then from here you have A is equal to EJ, EJ minus 1, E1 inverse times U. Or you can write actually A is equal to E1 inverse times E2 inverse times EJ inverse times EJ minus 1 inverse and times U. And this is nothing but the L. You see? So basically, in order to find the U, you need to use, a product of elementary matrices, right? That convert A into row echelon form. Is that right? And then you take the inverse of them, right? Of that product, you get the L. That's it. Okay? So we need to find the elementary matrices that convert A into row echelon form. Okay? So let's do this. The first one, I fix 1, I multiply 1 with negative 2, add to the third, right? I have A1 equal to 1, negative 3, 0, 0, 1, 3, 0 in here. I have negative 4 in here. I have 2 in here, right? And the elementary matrix, E1 is 1, 0, 0, 0, 1, 0. And here I have negative 2, 0, and 1. Means I multiply the first row by negative 2, right? And add to the third. You see? That's why we have negative 2 in here. Alright, so from here, I multiply the second row by 4 and add to the third. Right? I have A2 equal to 1, negative 3, 0, 0, 1, 3, 0, 0. I have 4, so I have 14 in here, right? So that matrix E2 should be 1, 0, 0, 0, 1, 0, and the third row would be 0, 4, and 1. You see, you multiply the second row by 4, add to the third. Okay? And now you can find this already, the U, right? In this case, that is U. So you can find the L. You can find the L. Actually, U is what? Is E2, E1, and A, right? By that, you have L is equal to E2, E1, the inverse. That is E1 inverse times E2 inverse. The inverse of E1 and E2 are pretty easy to find. Look at this. Uh, let's consider E1, right? You have E1 right here. So if you want to find the inverse of E1, you need to write 1, 0, 0, 0, 1, 0, negative 2, 0, and 1. And then here is identity, right? So you need to make this guy become identity. But you see, it's pretty easy. Because since here you have negative 2, you just need to multiply, the first row by 2 and add to the third. You see? And then you make this 0, and here you have 2. So this is the inverse. Similarly, you can find the inverse of E2 pretty easy, right? By, multiply the second row by negative 4, add to the third. So the inverse of E2, I can write E2 inverse equal to 1, 0, 0, 0, 1, 0, and here 0, negative 4, and 1. Right? And then you multiply these two matrices, you get the matrix L. Okay, let's do that. So I already have U, right? Where's U? U is right here. U is right here. Now let's find L. L is equal to E1 inverse, which is 1, 0, 0, 0, 1, 0, 2, 0, 1 times 1, 0, 0, 0, 1, 0, 0, negative 4, and 1. Okay, so what is that? You multiply, this is also elementary matrix, right? And this is what? That is multiply with the first row by 2 and add to the third, right? So you just need to do that for this matrix. Multiply this by 2, right? And add to the third. I will not do, like normal matrix multiplication. Yes, because I know this is elementary matrix. So I have 1, 0, 0, 0, 1, 0, and here I have 2, negative 4, and 1. You see? And that is the U. So A is equal to LU. Oh, the L, right? A is equal to 1, 0, 0, 0, 1, 0, 2, negative 4, and 1. Another matrix is U. Let me move this a little bit far. So I have 1, negative 3, 0, 0, 1, 3, 0, 0, and 14. That is the matrix A, and that is LU. Okay, the LU decomposition. Now let's apply this to solve the following system. X1 minus 3x2 equal to negative 5, x2 plus 3x3 equal to negative 1, and 2x1 minus 10x2 plus 2x3 equal to negative 20. So basically, if you pay attention, the coefficient metric is A, right? So I can write this is AX equal to B, where B is negative 5, negative 1, and negative 20. A is the one right here. Okay, and now let's use the LU decomposition to solve this, right? So I can write in here LU X equal to B, right? If I put Y equal to UX, then I have LY equal to B, where the L is triangular matrix. And we know that for triangular matrix, we can solve this system easily. So from here, you can find the Y, right? You can find the Y. All right, so let's find the Y for this system, okay? The L, where's the L? L is right here. L is 1, 0, 0, 0, 1, 0, 2, negative 4, and 1. So I have 1, 0, 0, 0, 1, 0, 2, negative 4, 0, times y, let's say that is y1, y2, y3, equal to negative 5, negative 1, and negative 20. From here, I can solve for y2. I have y2 is negative 1, right? And from this, I have y1 equal to negative 5, you see? And from here, I can find y3. I think I have something wrong here. 2, negative 4, 0. No, 2, negative 4, 1, sorry. So here should be 1, okay? It looks changed to me. So y3 is equal to negative 20 plus 4y2 minus y1. And that is negative 20 plus 4y2 is minus 4 and plus 5. So I have 4y2, interesting. No, here again, sorry, here I have 2, right? So here times 2, so that is negative 14. So you have y equal to negative 5, negative 1, negative 14. And then you plug this y into this equation. You have the system u. Here I have x1, x2, x3 equal to negative 5, negative 1, negative 14, right? Okay, let's copy the u. So you have 1, negative 3, 0. 1, negative 3, 0. Next one is 0. 1, 3, and then 0, 0, 14. You see, again, right, the matrix, the coefficient matrix is triangular, so it's pretty easy to solve. From the last equation, I can see x3 equal to negative 1, right? Because you divide, the third equation by 14. Since negative 3 is 1, I plug this into the second one. I have x2 equal to negative 1 minus 3x3. So that is negative 1 minus 3 times negative 1, and that is 2. And then you plug this into the first equation. You get x1 equal to negative 5 plus 3x2. So that is negative 5 plus 6, which is 1. So the solution is x equal to 1, 2, and negative 1. You see, actually, you may think about, if the coefficient matrix of some system is triangular, in this case, upper triangular matrix, in this case, lower triangular matrix, you can solve your system pretty fast. So that is the advantage of the LU decomposition. Okay, so overall, we use matrices. We use elementary matrices to realize row elementary operations, and we also use elementary matrices to factor a matrix as a product of two triangular matrices, and we use that to solve system linear equations. So right now we have 3 methods how to solve system of linear equations. I hope that the video is clear enough, and of course, I repeat again, right? The reason why they consider this, because they want to order the computer to solve the system of linear equations. So computer should understand all these row elementary operations. Okay, all right, so see you in the next video. If you have any questions, please feel free to let me know.